Welcome everybody to the presentation of field measurements of integrated MultiPACK supermarkets in Portugal. My name is Schlemminger. I'm presenting this work on behalf of the working group. I'm a researcher at Centre Energy Research in Trondheim, Norway, and I want to present you today an overview and a comparison of energy performance of two supermarkets. One is MultiPACK site in Porto de Mos in Portugal, and the other one is a reference shop, which is about 100 kilometers away. The presentation will be divided into several parts. First, I give a bit of a plant description and discuss the system layouts before I go into the measurement results, comparing the ambient condition of the reference site and the MultiPACK site, the electric power consumption for the different temperature levels, giving a short overview about the key performance indicators in the reference period we are looking on, and the effect of the ejector operation at Porto de Mos. So later. And then I come with a conclusion and a summary. Just to look on the plant side, what do we have at in Porto de Mos, and what we call a MultiPACK? The MultiPACK is basically a CO2 booster concept with parallel compression and expansion work recovery by means of different ejectors. Here we have both high pressure lift ejectors, liquid ejectors, and low pressure lift ejectors. Every one of them having a specific working task where I come into later on. The system is able to run in with overfed evaporators, as Danfoss is calling it, adaptive liquid control. What is a bit special here beside the ejectors is that the system is fully integrated also in terms of air handling, air conditioning and heating. So we have satisfying directly the heating and cooling demand into dedicated air handling units which are sitting on the roof of the building. Here we have direct evaporation of CO2 in the air handling units in the coils, or we have heat rejection also directly into the air handling units. What we also have included is domestic hot water production right after the compressor outlet of the medium temperature and auxiliary compressor train. The system has also a heat pump functionality, meaning in the winter time when the heat of the refrigeration part is not enough to heat the shop, then an integrated gas cooler here with an evaporation function as if for the heat pump mode is installed, so we can utilize heat from the ambient and lift it up to the desired temperature, which is required by the shop air handling unit. Further, we have the possibility to run dehumidification in the shop. The entire pack, as you see, is fully instrumented with both mass flow meters and temperature and pressure sensors. So there's a dedicated measurement system which we utilize for the MultiPACK system, beside, of course, the Danfoss controllers, which are controlling and monitoring the system as such. So we have access to both these measurement devices or control devices, so we can do comparison of different measurements. The shop as such has an area in the order of 2,400 square meter, and the complete installed electric power demand for the pack is about 177 kilowatt. If we take a look into the machine room, we see here on the right side the MultiPACK. So we see the compressor stages for the low temperature evaporation, the medium temperature evaporation, and the auxiliary or intermediate temperature compressors. As we see the mass flow meters which are installed in order to measure the mass flow rates in the pack. And we see the different ejector blocks as well as the high pressure expansion valve, which could be run in parallel. On the outside of the machine room is an integrated gas cooler placed, which I said in the previous slide, that this one can also run as evaporator in the heat pump mode. If we look at the reference side, the reference side has a bit of a different plant layout. Here we have a CO2 cascade with 134A on the top. So the CO2 system is providing the low temperature cooling for the supermarket, while condensing against the 134A circuit, which provides in addition the medium temperature evaporation level. This system is running Soleil on dry evaporation, and in addition to this, we have two separate air handling units. These air handling units are running independently of the refrigeration system in the supermarket. They have a dehumidification function, and data handling or data acquisition of the system is basically done based on the basic building management system and the compressor status, what we get from the control of the refrigeration system. The shop area is comparable in the order of 2,100 square meter, and the installed electric power demand for the HVAC and R system is about 230 kilowatt. If we look outside the shop, we see here on the left the two air handling units placed beside each other, while the machine room is on the complete end, and the condenser of the 134A units is seen here hanging on the outside of the south wall. As a summary, we can see here on the table that both the low temperature evaporation load, the medium temperature evaporation load, the AC cooling, and the heat recovery is dimensioned in the same capacity range, so this is nicely comparable. However, we see some differences. For example, the nominal evaporation temperature on the empty level is much lower for the reference side than for the MultiPACK side. If we count the number of compressors, we see that Porto de Mos MultiPACK side has a substantial lower amount of compressors installed, whereas the reference has 14 compressors. The installed electric power is 177 for Porto de Mos, while about 230 for the reference side. And what is important to mention here is that also that the MultiPACK side is fully scalable in terms of load ratios or capacities. So it's not necessary to have actually this load ratio deviation here. So it could also be much more or much less empty load or AC load or LT load applied. So this is comparing the measurement results of the MultiPACK and the reference side against each other. We see in terms of ambient temperature that we need to have a look on a period where we have comparable ambient temperatures. So we identified a week in June 2019, and we selected some days earlier June and mid-May in order to cover an additional temperature range for the comparison. We also tried to take the same weekdays in order to assume the constant or comparable occupant behavior. In general, what we notice is that the system is really transient, so we see the electric power demands of the systems are varying quite a bit over the period we are looking on. And in addition is that the allocation of the ambient temperature sensor is on high importance. Since we are using often the ambient temperature in order to compare the operation, the ambient temperature need to be measured in a very precise way. So what we, for example, see here in comparing Porto de Mos and the reference side is that we know for the reference side that the ambient temperature sensor is located on the southern wall of the shop, which is explaining this big variation. So in the midday when the sun is hitting the southern wall, the temperature sensor is showing much higher values than a sensor which is for example shaded properly. However, the load, at least for the LT and the MT evaporation levels, should be comparable because the air conditioning of the shop is in place, holding a constant temperature in the shop. By looking on the electric power demand of the system in the dedicated week, we see on the left side here that the MultiPACK system and the reference side, they have a comparable electric power demand for the low temperature compressors, which is plotted here in blue. There is a small difference between the auxiliary electric power demand, covering, so to say, some pumps and the air cooler, the gas cooler. What we see a bigger difference is the electric energy consumption both on the MT compressors. This is in the order of 10 kilowatt for the MultiPACK, while as for the reference shop, we are in the order of 30 kilowatt. And the same, we see also that the air conditioning electric power demand, or the power demand for the air conditioning, is much higher for the reference shop than for the MultiPACK unit. What is important to note is that the reference system is running at a constant condensing temperature for the 134A system, which is 33 degrees Celsius, while by adding an outdoor dependent condensing temperature, we could save already 15% of the electric energy consumption. What was also noticed is that the evaporation temperature of the empty side was rather low. In this case, it was minus 15 degrees C. So here's definitely also an improvement potential. However, this implicates, of course, that the evaporators, meaning the cooling furnitures, are designed in a proper way. If we look at the low temperature compressor power demand, which is here plotted over the ambient temperature, we see that they are very similar. So it's not a big deviation between the LT electric power demands. It is also that the increase over the ambient temperature is comparable. However, the reference shop consumes more LT power in the higher temperature than the Portugal side. If we compare the numbers of cycles, so how often the compressors are turning on and off, we see that this number is substantially lower for the MultiPACK side. It is in the order of 2.4 on and off per hour, while on the reference side it is 3.3. Comparing the MT power demand, so the medium temperature refrigeration power demand, we see that the MultiPACK side has a substantial lower medium temperature power demand than the reference side, and it is only slightly increasing over the ambient temperature. We also see that the number of cycles for the MT is in the order of 0.2, meaning the compressors are almost all the time on. And for the reference side, the compressors are very frequently being shut on and off. So here the number of cycles is in the order of 4.6. By comparing the AC power demand of the MultiPACK and the reference side, we noticed two differences. There is much lower AC power demand for both sides below 22 degrees ambient temperature. Based on the nature of the CO2 as a working fluid, we see that there's a small power demand also below 22 degrees C in order to handle flash gas from the evaporation. So here the frequency controlled compressor is used in order to recompress this flash gas, while at temperatures above 22 degrees C, we see an increase of AC load both on the MultiPACK side as well as on the reference side. However, the trend is comparable, but the absolute value is about 15 kilowatt lower for the MultiPACK side than the reference shop. So comparing the key performance indicators, which were set by the consortium, we see that the total specific energy demand of the MultiPACK system in Portugal is about 74% lower compared to the reference. Also, of course, directly linked to that is the total primary energy demand, which is also 74% lower. The peak power duration, so how much hours per hour the system is running on 100% capacity, is 75%, 57% lower for the MultiPACK unit. And the average electric power demand for the MultiPACK unit is about 70% lower in the same period. If we look at the LT load, we see, of course, a bit of a difference in terms of evaporation temperature. So the MultiPACK system runs with about 2 Kelvin higher evaporation temperature. Due to the system architecture and the monitoring, of course, we have no chance to say something about the load of the reference side, since we have no mass flow meters installed there. For the MT load, we see that there is a huge difference in terms of evaporation temperature. So while MultiPACK is running at 5 degrees C evaporation, the reference system is running at -15. So MultiPACK is running 10 Kelvin higher in evaporation temperature. And while for the AC, we see that the MultiPACK is delivering about 7.2 kilowatt at the evaporation of 1. Here we see also still a bit of increase of improvement potential for the MultiPACK side, because the desired evaporation temperature in the air handling unit is 10 degrees C. If we look at the energy efficiency ratio for this period, we see that the MultiPACK side has an energy efficiency ratio of 3.1. So the big question is actually how much does the ejector or how much do the ejectors together contribute to the energy saving? In order to indicate the effect of the ejectors implemented in Portugal, we were running several weeks of different operation modes. The first weeks were without any ejector in operation, only the high pressure expansion valve in operation. The second set of measurements were conducted with having the adaptive liquid control in operation, so minimize superheat on the empty evaporators and the liquid ejector, so to say, moving the liquid from the suction gas accumulator or suction gas separator back to the receiver pressure level and the receiver. The third set of measurements was containing the operation of both ALC, the liquid ejector, and the high pressure lift ejector. So here the high pressure lift ejector is recompressing gas from the suction gas accumulator to the receiver pressure level. And the fourth operation mode is, so to say, all the ejectors are on. So the liquid ejector, the high pressure lift ejector, and the low pressure lift ejector in operation, while the job of the low pressure lift ejector is to circulate liquid from the air handling unit and compressing it up to the receiver pressure. So the results obtained were that the ALC mode and the liquid ejector together contributed to about 17% of total energy savings. When we are comparing the operation of both liquid and high pressure lift ejector, we see that savings in the order of up to 25% of the total power consumption could be made. And by comparing the operation of all three ejectors to the non-ejector operation, we could identify that we are saving up to 32% of the total power consumption. So all in all, short summary, so the MultiPACK project is demonstrating the feasibility and performance of fully integrated CO2 systems in Southern Europe climates, in this case for Portugal. The effects of the ambient temperature and of course the consumer behavior of the supermarkets require an extension in the monitoring period, for example, a year or a year plus. So this monitoring is still ongoing. The analysis conducted indicate a big saving potential by utilizing fully integrated CO2 multipacks compared to, for example, CO2 and 134A cascade systems with separate air handling units. What is also interesting to see is that, of course, the combination of both high pressure, low pressure lift and liquid ejectors contribute to energy savings in the order of 32%. Thank you very much for listening this presentation of this European Green Week, and I would like also to thank you for spreading the knowledge about CO2